Hi, I work for the Bay Area Environmental Research Institute with a grant with NASA Goddard Space Flight Center, which is where this project is based. We're building a constellation design software tool to allow scientists who have an instrument or a satellite in mind. And what we want to show is if they can launch multiple copies of the satellite into space, how can they arrange it in space so that they can get science results that are better than with a single satellite. So this comes from a concept called distributed spacecraft missions, which is flying multiple spacecraft in coordination in space. The idea with distributed spacecraft missions is you improve performance because you can improve sampling in the spatial, temporal, and spectral dimension. It comes at a little more cost because you need more interoperability planning and better design at a much earlier stage in the design process. There's different types of distributed spacecraft missions. We have formations, constellations, and fractionated spacecraft. And what we're doing at Goddard is building a software tool to address some of the questions on how we can design for conflicting variables and objectives if you fly multiple spacecraft. So the software tool it's built in Python and C++. And the idea is the scientist or the program manager sits at the GUI, and he puts in science requirements. We have an executive driver that converts those requirements into class objects, and it generates a full trade space of search options for multiple constellation designs. And then the performance of those designs is evaluated in C++ and with a cost and risk tool, and finally written to disk. This part has been documented in previous publications whose references are below, so I won't go into that in much detail, but the idea is all of the user inputs are captured in a JSON file that looks like this, and it's divided into mission concepts, the kinds of satellite orbits that the scientist would like, the observatory, which is the satellite, and the instrument specifications that the scientist would like, and what sort of outputs that would be expected. And once the software runs, it generates a full file tree in the scientist's directory, and that gives him the results of the full search space of constellations. The types of outputs we have are fairly generic. We have things like the time it takes to cover the globe or the areas of interest, the time that each Earth point is accessed by multiple satellites, what's the time to revisit any of the points that are of interest, what percentage of the Earth has been covered. If you have latency requirements, how much time do we have to wait until we can get the data down to Earth, things like that. And all of this is given back to the scientist as global statistics or as local statistics, which is per grid point information. The kinds of constellations we're exploring, and I realize that this audience is not necessarily interested specifically in space, but the kinds of constellations that we're generating are homogeneous and heterogeneous Walker constellations. So specifically, that's a homogeneous spread of satellites around the Earth in a variety of orbital planes, which can be can vary in altitude and inclination. There's another type of constellations which is called precessing type. So the satellites get deployed in a single plane like that by a single launcher. But over time, because their altitudes and inclinations are slightly different, they spread out in orbit like that. So the advantage of this is that you don't need more than one rocket, which in Walker constellations, for every plane, you need an extra rocket. Another type of constellation, which I thought would be interesting for this audience that we've modeled, is called ad hoc, in which the single rocket delivers the entire load of satellites in one go, which was like the PSLV delivered 88 satellites in orbit a few years ago. And I pulled the data about 2 days after that launch, and all of the satellites are here, which means, so what you see in the radius axis is altitude, and the polar axis is mean anomaly spread in the same orbit. And all of the PSLV launches were here. But if you look at this data right now, they've nicely spread over the whole orbit. So that's an example of an ad hoc constellation, which we also model. So the purpose of this talk is to talk a little bit about the instrument trade space that we model as part of constellation design. So we're trying to answer questions like, what is the mean signal-to-noise ratio over a particular region of the Earth if we use instrument A on constellation X? If we change instrument A and make it B and fly the same constellation X, how does the result change? What if we use the same instrument A and you fly it on a different type of a satellite or a different constellation Y, things like that. So the results that I'll show here are in reference to a radar mission, a synthetic aperture radar, and we've published a similar case study on imagers in the last couple of years. So that's more in terms of visible and infrared imagers, but what we talk about today is radars. So what the instrument trade module does is it generates a trade space, just like the constellation trade space is generated by TAT-C, which is the original software. The instrument trade space is generated in two parts. One is non-operational specs, and once the non-operational specs have been generated, then we have operational specs. And you have many different designs of instruments, each of whose performance is evaluated using an instrument operation simulation model. So in terms of the search space generation, non-operational specifications of an instrument are basically specs of the instrument that cannot be changed once it's been launched and flying. So you have to design it early on before launch. So examples are, in the case of it, it's like the physical size of the antenna, or what is the maximum pointing maneuverability of that instrument. And then operational specs are can be changed once the mission is flying, and they're called time-tagged commands. So you send up software updates to the satellite, and it can change those parameters. So for example, if you want to change the duty cycle of a radar, that can be changed. If you want to change where the instrument is pointing at a specific time, that can be changed. So we have a full list of non-op specs and operational specs that can be modeled in the radar as part of our tool. So in the case of antenna generation, for example, you can generate different sizes of antenna, some of which are feasible and some of which we delete as infeasible in a filter. And then you have a valid search space, and that valid search space then goes to the instrument operational module. And then the operation module then generates, for every point of interest on the Earth, the minimum, maximum, and other statistics of an observation metric. It can be either revisit time, it can be signal to noise ratio, it can be noise, anything. So in the case of radar modeling, these are the parameters. I won't go into it in much detail, but there's about 20 parameters that we varied to look at the full design space of radars that you can fly. And some of the most important things in a radar is that in the pulse repetition frequency and the incidence angle trade space, there's a lot of areas where a radar is just infeasible because of an either echo overlap constraint or a transmit pulse overlap constraint or a Doppler constraint. So this is just in single instrument design. And then we translate this into multiple instrument design and then fly all those instruments in parallel in space. So in the single instrument design, for example, our tool is capable of showing the trades between PRF, which is pulse repetition frequency, and the pulse length in terms of signal to noise ratio. And all the white space is stuff where no design exists. So when we pick a design for a specific instrument, we have to choose a design in the colored areas. And at that point, I ask myself, what PRF am I happy with, and what do I need as pulse length for which I get a specific signal to noise ratio. And you can do these trades not just for these two parameters, but all of these other 20 parameters that I mentioned. And then you can vary altitude and so on. So here is, we do the trade for PRF versus signal versus incident angle for swath width. So that's another metric that's important because you want to have as much coverage as possible. So swath width is important because, especially with respect to all this, is just because you have a wide field of view sensor doesn't necessarily mean you'll get coverage. So that's for single instrument. So this is a very quick trade study that we did on multiple satellites with the designed instrument that from these results. So the latitudes we considered were between 30 and 60 degrees Celsius. We considered just a one-day mission duration. TAT-C is capable of doing much more. And we considered 2 satellite constellation with the conical spectral imager of 30-degree field of view. And what we varied was altitude between 500 and 1,000 kilometers, and the look angle, which is the angle at which the spacecraft is looking sideward direction, between 0 and 30 degrees. We considered 60 Walker constellations, which is homogeneously spread around the Earth, 1 in the single orbital plane, and we considered about half of them in a single orbital plane and another half in 2 different orbital planes. And TAT-C, as the tool that I described, is capable of showing the scientist or the mission designer how the access time, which is the amount of time that any grid point on the Earth can see any satellite with meaningful measurements. This varies as a function of look angle and altitude, this varies as a function of look angle and altitude. And from these plots, the designer can identify a point in this trade space that is interesting to him and he would like to go ahead with the mission design for. So we have similar things for spatial resolution, which is another metric. So the cool thing with TAT-C is that we can make these plots for any metric of choice and across any of the design knobs or design variables so that you can choose your final design. This is over many, many designs. Now, if you've chosen your final design or you have, say, 3 or 4 candidate designs in mind, for each of those candidate designs, you can then see the spread of, say, maximum incidence angle or different metrics spread over the Earth. So this is latitude in the y-axis and longitude in the x-axis. And you can see, so if you're interested in, say, South America or India, then you can see whether the metric that you want is a specific value over that specific continent. But this is, again, for a single DSM or a single constellation. Similarly, you can vary this over various look angles or design specifications and see whether you get your results as expected in a specific geographic region. So the summary of this is that we're developing software tools for pre-phase A design of constellations for Earth observation. And TAT-C is the name of the tool we're developing. It allows such investigations by allowing users to optimize constellation designs with respect to priori science goals in a very user-friendly way. We've published some of this, especially about the software in previous literature. And if you have questions on that, I can point you to the references or I can talk to you after this talk. But in this talk, we talked about the SAR instruments that have been incorporated into TAT-C's instrument module. And for the future work, we are developing a more sophisticated search space generation tool than just full factorial, like generating all the possible designs. So we're using machine learning to sort of find the design in a more intelligent way. And we're also planning to put in other instruments like radiometers and lidars. We also have a parallel project that's going on, which optimizes schedule for steering instruments in an autonomous way, either with ground computers or onboard autonomy. And that's part of being able to verify, so validate and verify the operational analysis of satellites.
Okay. So we have time for some questions.